All right, so I'd like to, so I think this is a good review of complex numbers a little bit, and we'll have you get your legs under you on some of the other ones on there too, require some other techniques you might remember from Algebra 2. So, if you, like I said, if you're trying those, you can do those. We'll have people come up and do those in a minute. But hopefully, have we done it here? Have we written all of these in a plus bi form? Something real plus something real times I? That would be the goal. Right? So this shows me you remember something about complex numbers. I thought I'd share this with you. This is Mr. Davis is someone who you'll have someday for math if you take HL or, yeah, hopefully everyone's lucky enough to have Mr. Davis. He's a wonderful teacher. Or maybe you have some contact with Mrs. Davis, who's the theater person, right? If anyone does anything related to theater, you'll meet Mrs. Davis. They're both wonderful people. I was in their wedding, and this was my place card at their wedding. Can you tell me what table I sat at? -1. I sat at table -1, yeah. Not all of the cards had problems that were that difficult on them. You know, but for the normal people, right? They had other problems that were easier, I think. And actually half of them were not math problems, but like, I think like match the book to the author or something like that, and maybe you were sitting at table like Hemingway, or I don't know what. That was the name of your table, something like that. Miss Jessel took a cue from that recently too. I'll have to show her some of the pictures of her table. I actually went around before anyone came into the reception hall, and I took photos of all the table decorations, because I sat at table mu actually, but they were all math there because they were. I know. I felt like I was like, wait a second, why am I at the average table? I was like, that's a little. I was like, That's true. That's true. Maybe I'm coefficient operation. They were thinking math things though, not physics things. All right. So like I said, I'd like to have some people come up and put. We'll start by just putting. I have 2 slides of those problems. So let's do that first. And I'll take some volunteers on these. That's fine. That's great. So here we go. All right. So I don't know whether Simon got that one right or not. Can you tell me? Anyone else get that same answer? Yeah. All right, it's terrible, but it worked. Okay. If you do that, then like you're probably doing pretty well on all the things you learned from Algebra 2. Well done. This one again comes out really nicely. F comes out nicely. Remember how to multiply by the conjugate to get rid of the denominator. So all these things from Algebra 2 that you should remember. Okay, that's the story on these first couple slides. And then we also have something that's happening too. There's something afoot with F and also C on the warm up. There's something weird happening. We just discovered a cube root of 64i. Wow, cool. All right. All right, so let's say something about complex numbers going on with our discussion. We were just talking about kind of the history of complex numbers a little bit. So my question would be, where does 1 plus 2i belong, for example? Or you might ask, which number is bigger, 1 plus 2i? Or how about 2 minus i, or something like that, right? Can we compare these? Like if I were to put a greater than sign here, or a less than sign, which should it be in between those two, right? This is a good question. What do you think? Has anyone ever even asked you that before? Of course, where does 1 plus 2i belong on this number line? We can actually kind of be honest. What is this called? It's called the real number line. So the answer is, of course, nowhere on that number line. That's the real number line, and this is not a real number, so it doesn't belong there. Instead, it belongs, we're going to visualize these as points in a plane, right? So you almost think of complex numbers as, there's nothing imaginary about any of this. They're just 2-dimensional numbers, that's all. That's all. There's 2-dimensional numbers. We have, instead of the x-axis and the y-axis, we'll call those the real and imaginary axis. And then when we have a number like, we'll say this complex number z, we might even write, instead of a plus bi, we might write x plus yi, right? Just to emphasize the fact that this can be thought of as the point x comma y in the complex plane. So there's z. Everyone okay with that? And this is called the complex plane we're looking at, or sometimes we call this an Argand plane or an Argand diagram, sometimes people say. So this is helpful in understanding how we might think of a complex number in a more concrete way. Right now we can put it on paper. And that makes I really not like some ethereal thing. It's really just the point. 0, 1. That's all I is. Okay, it's just another name for the point 0, 1. Yeah, sure.
X and Y is still axis or point on
Yeah, I'm using x and y to mean particular values. Yeah. We might also ask about the magnitude of a number, and by that I mean the length of this segment from the origin. Okay, I'm using the magnitude kind of like in using vector speak here, right? So how long is that line segment? Of course. How do we find the length of that line segment? Of course, it's the Pythagorean theorem, or right? Root x squared plus y squared. I'm also using this notation with the vertical bars to evoke, what else might we call this? We might call this the absolute value of a complex number, or sometimes we also call it the modulus. I'll put that up there as well. So 3 names for the same thing. But absolute value is a good way to remember it, right? Because you've done this before. We've thought about this with vectors too. Why is that a good notation? Well, because absolute value you understand as being the distance from 0. So this generalizes nicely to the 2-dimensional complex plane. And again, we should say, instead of we called it in the world today, we called it a plus bi. We said put these in standard form. But we could also just as easily say, let's start calling that rectangular form, right? X plus yi. Is that good? Yeah.
Just like as a general matter, is it x squared plus y squared as in yi? Like y the point?
No, just x and y, the real numbers up here. X and y are real, right? We often abbreviate this RE and MI, IM rather. So let's plot 8 minus 15i and also find, please, the absolute value of this complex number, or the magnitude. I'll plot it. How about, and you guys find the magnitude? That'll be the easy part. My board issue. Anyone come up with a magnitude then? What's 15 squared? 225 plus 64 is 9. You know your perfect squares? I like to surprise you and delight you once in a while. Okay. Or maybe you knew that Pythagorean triple. Yeah, it does just come out to 17. Yeah. I'm gonna go for the exotic Pythagorean triple once in a while. Okay. Doesn't get a lot of love. That one. Rather. There are lots of infinite numbers.
Are there an infinite number of Pythagorean triples?
Yes, and that's a trivial question to answer because all you have to do is keep multiplying them by 10 or something.
But if they're like unique ones.
Yeah.
Yes.
Yeah, primitive ones, they're even an infinite number of primitive Pythagorean triples too. Yeah, there's a way you could generate them using some formulas. We could teach you how to do that. All right, so if I've gone out of my way to call this rectangular form, then maybe we should also be able to put these in polar form. Absolutely, right? So we can just make the following substitutions, which are no surprise. X is just r cosine theta, and y is r sine theta. The big question is like, okay, I get it, but why are we doing this? And I won't tell you today, okay? It's just for fun. Let's see if we can pull it in polar form. Okay? So here's polar form. We can factor out that r if you like, but this should not be a big surprise. We can write a value z if it's complex as r cosine theta and I sine theta, where r and theta are the same r and theta we've been using all along in polar coordinates, right? Sometimes because we're going to write this so often, if you want to write z equals r cis theta, you're welcome to, and we'll just understand that to mean whenever you write it, cosine theta plus I sine theta. Is that it? I know it's kind of weird, but I don't know if that's universally recognized or not. But and of course, like I said, r is still the square root of x squared plus y squared. That's what r is, just like we know it's always been. Now we could also call r the magnitude of z, though, too, right? Those are the same thing. And theta is the angle, right? And there's a discussion about how to find theta, but we've had it a million times, right? If I give you an x and a y, you should be able to tell me what r and theta are, right? We just did it on the quiz. Sometimes the angle theta is called the argument of our complex number. So we can write complex number in a plus bi, or we can write it in modulus argument form, right? With r and theta instead. Yeah.
Are we gonna get to the point of doing this?
We are eventually, but not today. Yeah. Yeah. There's some beautiful results. Euler comes back into play here today, obviously. So we'll do a conversion here in a second between rectangular and polar form, but it will have no surprises for you, right? It's just the same as if we were converting coordinates from polar and back, right? So today I just want to say, like, hey, this is possible. Just write it in polar form. Yeah.
In that two-dimensional numbers, then we have three-dimensional ones.
Sure. Yeah. Yeah. I mean, we'd have to talk about what meaning that might have and things like that. But can you establish? The bigger question is, of course, we can have like 3 or 4 to 5 and 6 n-dimensional numbers. We can call them vectors, right? The more important question would be, could you establish an arithmetic of some kind with those kinds of numbers? Do you understand? Because we have that for 2-dimensional complex numbers. And that's a good question. And the answer is yes for certain dimensions, but not all. Yeah. All right, so like I said, no surprises here, but let's convert this to polar form. X is negative 320, and so is y. So even without a calculator, I think we should be able to establish what the polar form will be. We need to figure out what r is. So that's going to be root x squared plus y squared. And what does that come out to, of course? Well, I shouldn't say of course. Yeah, it's just 320. Have you done enough 45, 45, 90 triangles to know that's just 320 root 2? Okay. You can actually work the algebra out too. It'll agree. And what's theta? Picture it, maybe. Let's just picture it together, isn't it? Aren't we down here in fourth quadrant, in the third quadrant? Boom, boom. Yeah, 5 pi over 4, right? I mean, you can also kind of run some formulas and think about, take it to your calculator, do the inverse tangent of 1, and then add pi, right? All that. Feel free. But you will get 5 pi over 4. I think we can all just visualize that too. It's in the third quadrant. Okay. So how would we write this? You could write this as z equals 320 root 2 times cosine 5 pi over 4 plus I sine 5 pi over 4. And we would consider that polar form, right? Can you go backwards? Yeah, just evaluate those two things. You don't have the same thing. Going backwards. Like I said, if you want to abbreviate that and write just 320 root 2 cis 5 pi over 4, you could. Just because we're going to write this so often, this gets a little cumbersome.